Good morning, everybody, and I am looking forward to a very dynamic and exciting conversation with our next panel. I'm going to invite everybody to come up. It's going to be with us, so Dr. Don Scavia. I have Melissa Millett with Clean Wisconsin, Kurt Hayland, and Chief White. My name is Dareth Glantz, Commissioner with the International Joint Commission. Long time in my previous, before I joined the Commission last year, I was very active with the Healing Our Waters Coalition, and it's wonderful to see how large this has grown and how effective coming together with collaboration works time and time again. We have a fantastic panel, and I want to spend just very briefly talking about who these folks are. They're going to each get 15 minutes. We're going to stay on time because what we really want to hear are your questions and answering your questions on some of the most incredible challenges facing the Great Lakes, which is nutrient pollution. In 2011, we saw the absolute worst algal blooms ever in the history of Lake Erie. We thought we had addressed this problem, and the ecosystem has fundamentally changed, as you know. And our panelists are the practitioners and the experts that really will be able to give us the insights that need to be what we need to know about the science and the policy to address these problems so that we can ensure that our Great Lakes thrive today, tomorrow, and forever. So it's my great pleasure. I'm going to just give a brief overview, and we've changed the order up a little bit. But first, we're going to have Dr. Don Scavia, who is with the University of Michigan. We have benefited greatly from his expertise. I am so glad that he's here today. He is a dynamic speaker and knows more about what is happening with nutrient loadings and the way that the lakes respond than anybody else. He is one of our key members of the IJC Lake Erie Ecosystem Priority and an inspiring, hopeful bearer of some very challenging news. So without further ado, I'll have Dr. Scavia give his presentation. Thank you very much. So while we're waiting for the PowerPoint to get started, I want to make sure that you know that this is as interactive as possible. We have a number of microphones throughout the ballroom. So when it's time for questions, we're going to have folks line up. We also are accepting questions via email. So if you just email healthylakes@gmail.com. We've received a number of questions so far, and we are hopeful that this conversation, the goal, we know that 25 minutes of questions are not going to answer all of the questions that we have, and this is a continuing conversation. So again, that's healthylakes@gmail.com, and this is just the beginning of the conversation. And I believe we're ready to get started.
Well, thanks for the introduction, and I'll try not to get all geeky on you, but I am actually going to show you some data slides. I want to start just by acknowledging the two major funders of the work I'm going to be talking about, the NOAA's Center for Coastal Sponsored Ocean Research and the National Science Foundation. And note that, in fact, the NOAA grant was awarded over 7 years ago, and I'll come back to that in a second. The team from both these grants are from the academic community, primarily from these universities. There was a lot of discussion yesterday about binational, bipartisan, and bicameral, but that's nothing compared to this. We even included Ohio State. So the upswing on this curve is a representation of the bad old days. The downswing is a representation of the good old days, when the size of the dead zone in the central basin of Lake Erie was decreasing in response to the Clean Water Act and the original Water Quality Agreement. That dead zone continued to decrease in size until the mid-1990s when something happened. And this is what we really need to talk about and what we're going to be exploring today. Another way of looking at this, rather than the size of that dead zone, is the rate of oxygen depletion. which again, that depletion rate declined until the mid-1990s and then started to come back up again. A little circle is going to represent in the mid-1990s, and that'll come up many times in this. And it's not just the central basin of Lake Erie, the western basin, harmful algal blooms, the large, massive blooms that Dareth mentioned, again, were on the decline until the mid-1990s, and then they resurged since then, particularly with the cyanobacteria, which is the microcystis, the harmful algal bloom that we've been talking about. And you've probably seen this graph from Tom Bridgman looking at the overall biomass of microcystis through 2010, and then with 2011 put on the graph, we all experienced that horrible event. This is what it looked like in the Western Basin. We've seen slides of this. This is how it spread into the Central Basin. If you went to the beach here, it looks pretty nice. If you're here last year looking offshore, it was not that nice. 2012, there's almost no toxic algae out in the Western Basin and nothing spreading into the Central Basin. And if you're wondering why that might be happening, if you're to compare the 2011 spring phosphorus loads from the Maumee to the 2012 loads, it gives you a hint of where all our work needs to be done. That's not caused by management actions, it's caused by drought. So what matters to hypoxia? First of all, the thickness of the bottom layer in the Central Basin matters. If it gets very, very thin, you have very little oxygen to start with. That's controlled by air temperature, winds, and the length of the season itself. It's also controlled by the amount of organic matter that settles into the bottom, because it's that organic matter coming from algae, stimulated by phosphorus, that decomposes and uses up the oxygen. So what matters to the harmful algal blooms in the Western Basin? Pretty much the same sorts of things. Air temperature, wind speeds, and the length of the season mattered, but also the phosphorus loads that stimulate the algal growth. So we want to combine those two ideas, those two sets of problems into one set of solutions. So the fundamental question that we were addressing and that we need to focus on is why we had this turn of events in the mid-1990s. What's happening that's causing a degradation of what we thought was a solved problem? So we want to talk about phosphorus supply, but first let's take a few slides to ask why this matters and who cares. Just a few images of the harmful algal bloom in the Western Basin is about all we need to say about this. The impacts on water quality, on the drinking water, the requirement to treat drinking water, the aesthetics, the impacts on tourism are obvious. The effects on the fisheries are a bit more subtle, and we've actually been looking at that. This is two set of graphs. The upper left-hand corner is the smelt relative abundance as a function of the duration of hypoxia in the Western Basin. So you can see as we get more and more longer duration of hypoxia, larger extent of hypoxia, the relative abundance of smelt is decreasing. But in the bottom right-hand corner, we have a graph of the actual commercial catch of smelt as a function of hypoxia. And in fact, it increases during this time period. What's happening is, and I'll show you one more slide, is that the smelt are being aggregated and becoming easier to catch. This is a graph of the abundance of smelt. You can see they're well distributed, the multiple colors is well distributed as the lake is starting to warm up. When the lake warms and gets very warm at the surface, the smelt want to go to the bottom because they prefer the cold water. What's happening is they're being squeezed. They want to go to the bottom, there's no oxygen, so they can't, so they're being squeezed into this very thin layer, making them much more vulnerable to catch, also removing them from their preferred habitat. If we look at yellow perch and walleye, this blob is actually the Central Basin. The yellow perch and walleye, this is the distribution. You would have them in September. If you have no hypoxia, this is where they would end up by the end of September in their preferred habitat. If you run this model again with hypoxia in place, you can see that they're being removed from their preferred habitats, being pushed closer to shore, forced to eat different kinds of food, and forced into less suitable habitats. So who cares? There's clear harmful algal bloom impacts on the drinking water and on tourism. There's more subtle impacts on the fish, but it's reducing the quality of their suitable habitat, altering their distribution so they avoid those zones. They're switching to novel prey. The yellow perch are eating zooplankton rather than their preferred benthic prey. They're more susceptible to catch. The models are suggesting that all of these are leading to reduced growth and reduced productivity. So it matters to the fish as well. So do phosphorus loads matter? couple of very simple graphs hint at this. This is the abundance of the harmful algal bloom microcystis as a function of the phosphorus loads from the Maumee River through the 2000s. Very strong relationship between the two. This is a graph that I was showing that oxygen depletion rate earlier, and I put on the graph here the dissolved reactive phosphorus load from the Maumee and the other basins from the mid-1990s. You can see the very strong correlation between those. So phosphorus does appear to matter dramatically for both hypoxia and for the harmful algal blooms. So we heard about looking at new targets, looking at the potential for developing new targets, and the renewed water quality agreement says we need to do this sometime in the future over the next 4 or 5 years. So can we set these target loads? It's a really interesting piece of work that's just been completed by NOAA, looking at the relationship between the intensity of the cyanobacteria, the harmful algal blooms, as a function of the phosphorus loads and the spring discharge into the western basin. The left-hand graph here shows the relationship between the intensity of those blooms and phosphorus load from the Maumee in the spring. But also showing the relationship between these blooms and the spring discharge. So there's a combination here of the phosphorus stimulating the bloom. This discharge is actually helping move it throughout the basin. This model was actually put in place to develop a prediction of the size and the intensity of the bloom in each particular year, and the model produces a pretty good fit to the observation. So we actually have a tool now where we can actually look at the discharge of phosphorus and flow into the western basin and predict the size of the bloom this coming year. Also can be run in scenario analysis to help set targets. By the way, this was the blind prediction for 2012, which was pretty good. The more complicated problem of hypoxia in the central basin, we've built what's actually a pretty standard eutrophication model at this point. In time, calibrated it to the dissolved oxygen in the central basin. These are just graphs showing the relationship between the model output and the observations, showing that it does actually reproduce what's happening in the lake over these past several decades. And we're now actually able to develop these response curves, where we can predict the areal extent of hypoxia in the western basin as a function of either the total phosphorus load or the soluble reactive phosphorus load. Now, I'm a bit coy here by putting no numbers on these axes, because we are still testing and validating this model, but we're ready to have this completed in the next few weeks. And when done, we'll be able to take a particular hypoxic area extent that society assumes is something we're willing to accept, and set new targets and identify what the new target loads ought to be to Lake Erie for that purpose. So I wanted to make a subtle point here, so I use very small font. But given what society will eventually decide as acceptable harmful algal bloom abundance and hypoxia, we can estimate the required target loads very soon, like within the next few weeks. This is now several years before what's called for in the Water Quality Agreement. And this is what I would like to emphasize as the value of anticipatory science. This was stuff that was put in place 6, 7 years ago, anticipating the problems. It's the kind of work that the Great Lakes Restoration Initiative ought to be supporting, so the next $1 billion is actually spent more effectively than the first $1 billion. And I want to take a second to thank the Healing Our Waters Coalition for supporting the idea that science needs to be strengthened as we move forward. Well, setting targets is actually pretty easy. Meeting them is a bear, as we all know. And the speakers following me are going to talk a bit about that. But we also put in place programs looking at where is this phosphorus coming from in Lake Erie. And so we looked at all of the watersheds around the entire lake and did phosphorus balances, looking at how much phosphorus is coming into those watersheds and where does that phosphorus go, so we get a sense of where to actually target our activities. And this next set of graphs gives you an indication of the primary input of phosphorus into those watersheds. And it kind of goes around the basin looking at different kinds of watersheds. So if we look in the sort of the Canadian eastern part, most of the phosphorus going into those watersheds is going in as animal manure. If we look at the more populated areas around Detroit, Cleveland, and others, most of the phosphorus going into those systems are coming in as human phosphorus, human loads into those treatment plants. And then if we look at the agricultural basins, the predominantly western basins, most of the phosphorus going into those watersheds are coming in as fertilizer, phosphorus fertilizer. So they looked at these balances, and they actually looked at them over time, over the last 6 or 7 decades, to see how things are changing. And the conclusions from that set of work is that the nutrient additions actually to the land have declined over time. And the export of nutrients as food and feed from those watersheds have increased to the extent that the difference between the amount of phosphorus coming into the watersheds and the amount going out is actually pretty close to balanced at this point in time. So we're really moving it in the right direction, but there's a lot of phosphorus stored in those watersheds, which is leading to the problems we have now. And the fact that location matters. It's different whether you're in the big cities or you're in the northeast part or the southwest part of the watershed. So many of you, I'm sure, have seen this kind of graph of what's happened since the Clean Water Act and the original Water Quality Agreement. Most of the reduction in phosphorus loads to the system have been through reduction in point sources. What we're left with mostly are non-point sources. And of those non-point sources, at least during the 1980s, most of it is in the particulate form of phosphorus, whereas only 18% was coming in dissolved. The problem is actually perhaps a bit easier than most of us think when you look at where we have to focus our attention. The size of the arrows going into Lake Erie here represent, to scale, the amount of total phosphorus that goes into Lake Erie. So by far, the Maumee watershed and the Detroit River are the largest sources, with Sandusky close behind, in total phosphorus. In soluble reactive phosphorus, the kind of phosphorus that's most readily available to algae, it's pretty much the same, the Maumee and the Detroit River. So it was very good to hear a discussion yesterday about the Farm Bill, about the ability to start targeting some of our resources. I want to have one point here that is often missed, because when you look at the Detroit River load compared to the Maumee, they're quite comparable, and it often immediately points to the Detroit water treatment plant, which is an issue, which is something that needs to be addressed. But the Detroit River accounts for 40% of the load. Of that 40%, 23% is still non-point sources from the St. Clair watershed and from the larger Great Lakes watershed. 16% is from point sources. So we're dealing with fundamentally a non-point source issue throughout. Now, in the 70s and 80s, a lot of the activities that was put in place to deal with non-point source pollution was focusing on particulate forms of phosphorus, because that was the predominant form going in. And those programs were actually quite successful. You can see this is a reduction in the amount of particulate phosphorus coming from the Maumee and the Sandusky River during this time period. So those programs put in place were quite successful. But the dissolved reactive phosphorus, the form of phosphorus most readily available to algae, did this sort of iconic turn of events in the mid-1990s. This form of phosphorus is the form that's most readily available. It's the form that's stimulating the algal production in the western basin and the algal production that's in the central basin, and the part that we need to focus most on. So the results from that sort of part of the analysis was that the total phosphorus load fluctuates depending on the weather, depending on whether it's a drought year or a wet year, but there's very little trend overall. The particulate load of phosphorus for a given discharge has been declining over the decades. But this dissolved form, this dissolved reactive form is increasing since the 1990s. There's lots of different implications about that, and I'll come back to that in a second. To look at what's causing this potential change overall and to look at the effectiveness of the current programs we have in place, we built and calibrated the soil water assessment tool, SWAT models, for 6 of the major watersheds. And this is a tool that's developed by the USDA and used for analyzing the effectiveness of BMPs in these watersheds. And we ran this model. After calibrating to the system, we looked at a whole bunch of different scenarios of best management practices, and we looked at it under a series of potential future climates, a moderate climate change or a severe climate change. And this graph shows the results. Each row is for a different watershed. Each column each column going up represents a different watershed. Each row represents a different combination of best management practices, with the baseline being furthest to the left and a whole series of different alternatives for best management practices for no-till, cover crops, filters, and combinations going to the right. And if it looks to you like there's not very much of an effect of these current best management practices, you're correct. What we put through the model is what the agricultural extension folks and the NRCS and the producers in the region consider feasible best management practices given the current programs, the current incentives that are in place, and the current funding that's available. Our conclusion from this is that it's not very effective at this point in time. In fact, if you look at the yield reduction effectiveness from the Maumee watershed alone, with these different implementations of best management practices, the feasible approach that we looked at here is only giving you about a 5% reduction in the overall load. We have to get much higher than that, and we hope the new Farm Bill will actually move us in that direction. We did hear quite a bit about it yesterday, increasing the conservation, targeting the measures in the area is going to be critically important, and so hopefully we can get higher implementation over time. I'm running out of time, so I'll skip this and get to the final part here. We really want to look more closely at what was causing this upswing in the dissolved reactive phosphorus load since the 1990s. So we took that same SWOT model and we did it at a much higher resolution in the Sandusky so that we could ask some very specific questions. We calibrated that model to 40 years of observations of the load into the, from the Sandusky, and got a model that pretty much does a pretty good job of representing the overall trend, but very much catches that upswing. And then we started asking questions of that model. We looked at how does a fertilizer application rate impact this? And of course, as you add more and more fertilizer to the system, you're going to get more load coming out of the system, but it didn't really affect this upswing in trends, whether you have constant high fertilizer or low fertilizer. We looked at the no-till practice, the practice of not tilling the land to see whether or not this was having an impact. And as we're beginning to learn, no-till is tending to actually increase the amount of soluble phosphorus going into the system, while it's continuing to decrease the amount of particulate phosphorus going in. So there was that increase overall, but it really didn't affect that upswing in the final years. We looked at the vulnerability of phosphorus to be flushed off of the system as an impact of no-till and other practices. So there's a term in the model that we can do to sort of increase this vulnerability. We did that, and we're actually able to reproduce a bit of the upswing by including that property, but there's still something very strange happening in this last decade. So we all know that there's been increased storms, increased intensity of storms over the last decade or so in the region. So we ran a very simple test through the model. We had actual weather, which is what we put in here in the blue, and then we just reversed the weather. We took 2010, put it in 1970, 1970, put it in 2010, and reversed it. And what happened was we lost that upswing in the recent years, and not very much changed in the early years. And so what that's telling us is that weather really matters now, but that same weather, if we applied it decades ago, didn't have that same impact. So our conclusion, here it is that the watersheds appear to be more vulnerable to these weather impacts than they were decades ago. That the high accumulation of phosphorus in the surface soils and the tillage practices might underlie why this increased climate-induced weather is causing this upswing in the loads. The overall fertilization rates matter somewhat, but not to the overall change. We all know that we're going to get longer growing seasons. We're getting more intense storms, getting more precipitation in the future, so this is going to get even harder. So my closing remarks here is that hypoxia and the harmful algal blooms have actually increased since the 1990s. It does matter to drinking water, to tourism, and to fish. The increases are likely reflective of the increases in the soluble reactive phosphorus load, which appear to be driven by this conspiring of this new weather regime we're in and the current agricultural practices. The current suite of best management practices, as they're being applied, are not sufficient. Climate change is going to make it even more difficult, and we may need a whole new suite of best management practices focused on phosphorus runoff in the new regime. Thank you.
Thank you. The science is so critical. I've had the pleasure of seeing Dr. Scavia give his presentation several times. Every single time there's more important information that is included, and I'm very hopeful that those targets that we're going to get very soon will be able to far exceed the expectations in the Great Lakes Water Quality Agreement, because it looks like we need to double down, if not triple down, our efforts. It is my great pleasure to introduce our next speaker, Mr. Kurt Hyman. Hyman. Thank you very much. It's right there. He's going to correct me. Has been with the Soil and Water Conservation District for over 24 years, and he is a farmer. So he works with the land and is the resource manager on the ground, making some really significant progress. He and his family raises corn, wheat, hay, straw, soybeans, popcorn, and cabbage, as well as commercial hay and straw operation. And I really look forward to his comments on what we can do on the land to benefit the Great Lakes. Thank you very much. Now, while we get the presentation up, we really want to make sure that we reserve time for questions. So you'll see me coming up to you very closely if you go over your time. And these are folks that spend their entire lives working to protect the Great Lakes, to do what we need to learn about to implement throughout the entire basin. And we've asked them to do something very challenging, which is to put this all within a very small, tight 15-minute time frame. So I recognize that it's a very short period of time, but we want to make sure that we're able to hear from everybody. And so I'm going to do my best to keep us on track, as long as technology helps us. So while we're waiting, I'm going to ask you a question, Dr. Scavia. Yesterday, well, actually, I think it was on Monday, I listened to a great presentation by Dr. Jeff Reuter, and he indicated that he thought about a 2/3 reduction in phosphorus loading is what we needed to do for Lake Erie, and I wondered if you wanted to speak to that general idea. It's been something I've been thinking about.
You know what? I think I'd actually hold off on that. I think our models are ready to do that.
Yeah.
2/3 probably gets us back to what it was like when we had the good old days. But we have to look at the difference between the total phosphorus and the soluble reactive phosphorus, so we'll do that.
Excellent. Thank you. Go ahead.
All right. My name is Kurt Hyman. I'm with the Erie Soil and Water, and also a farmer, and I think that's my biggest credential. Dr. Scavia, I think I should have seen that a long time ago. That's put a lot of different thoughts in my head. It's kind of might even change my presentation a little bit. We're probably adding to the problem because we've been in no-till, and we solved the sediment problem, but we haven't solved the dissolve problem. We're located mainly in Erie and Huron counties. This picture happens to be along State Route 13, about 3 miles south of Lake Erie. It's combining winter wheat, and we're going to end up planting double crop soybeans in there. They ended up going about 45, and the wheat was about 80, I believe. That was 5 years ago. One way that we manage our nutrients is we have several different crops, so we have a little bit different crop rotations than most people. A couple of real long ones, wheat and alfalfa and wheat and timothy, and they end up giving us a pretty good cover crop ratio without having a cover crop. And really they're better than an annual cover crop because they're perennials and do a lot better job of growing in the off season. I'm going to kind of concentrate on the fourth down rotation. That's wheat, cover crop, corn, beans. That's a significant part of our acreage. We usually have a cover crop there 2 out of 3 years, the wheat being one of them, and cover crop the next year being the second one. A lot of our crops are harvested kind of late in the season, and since we're so far north, sometimes it's hard to get a cover crop established because we don't harvest corn until November. I'm going to just talk about one field. guess I don't have to look up, I got it right in front of me. It's located about 15 miles south of Lake Erie. It's in the eastern branch of the Huron River. It's predominantly Bennington and Cardington soil types. It's been tiled about 8 years ago. It's at 40 foot. There's 2 outlets, one to the kind of to the northwest, and then down on about halfway south of the buildings on the west side, there's another outlet. We'd kind of like to put some drainage control structures in this field, but it's got a little bit too much slope. I don't think we'd be able to take care of it that way. In 2011, the field was in wheat, and after the wheat and the straw was harvested, we had a Sunrise Cooperative take a grid sample of the field, which we have done on this field, I think, 4 or 5 times now over the past 15 years. And they give us a pH, organic matter, phosphorus, and potassium levels, and also cation exchange. The first thing they do is make a lime recommendation for us. This is what we applied last year. The one on the left is the recommendation, and the one on the right is what the equipment actually did. So the equipment's pretty accurate. It really does what they say it does. That's just a picture of them loading up lime. Now, since all this algal bloom stuff has started, in the past, agronomists pretty much told us that P and K were pretty stable in the ground, as long as you didn't put them on frozen ground or right before we have a flood or a heavy rainfall. So we'd put a lot of P and K on in the fall. The fields are dry. That was, and it's cheaper then, and if we usually could get it done before it got frozen. And at the beginning, we'd put corn and soybean fertilizer together. Fertilize the corn, and then the soybeans would use the residual fertilizer. Well, a couple years ago, I started thinking that maybe that wasn't the best way. One, you're putting a lot on at one time, and 2, maybe the soybeans would benefit better from annually. So we kind of switched to annually. Some applied in the fall, some applied in the spring. Last year, we even, since it was so wet and we didn't have it all done, we even planted first and then put the fertilizer on. And that's probably going to be the way we're going to have to go in the future. But to do that, we'll have to get our own fertilizing equipment, because there's not enough equipment in the area to do it all at planting. But I think if we had our own fertilizer storage and our own spreader, I think we could probably do it. Then we plant the field. We usually plant 2 varieties with the idea that you can never predict which variety is going to do better. So we get ones that are a little bit different maturities, a little bit different genetics. That way, if the season favors one, at least the whole field isn't the wrong one. And over time, I think that's a better strategy. And a lot of times, if the earlier variety, if it's a short season where we didn't have a lot of growing degree days, the shorter season variety is drier, and it costs less to dry the field then. Since we have longer rotations, we've stuck with pretty much non-GMO seed. We don't feel we need the insect control because we don't have an insect problem because we're in a long rotation. And the herbicide trait, we're rotating our herbicides pretty heavily so that we don't have weed resistance problems, so we change every year. The nitrogen, the way we handle that, we put about 30 pounds on with the planter, it's 28%, and then we side dress the ammonia, anhydrous ammonia, after the corn is up, anywhere from up to knee high, depending on if we can get the work done or not. The anhydrous ammonia is much more stable in the ground once it's in the ground, and it's much cheaper per pound. All the other fertilizers are derived from anhydrous ammonia, so that's always going to be the cheapest one. And there's a lot less to haul around because it's 82% N versus 46 or 28 for other common materials. Oh, here's something I forgot to mention. Before we planted this corn the fall before, last August, basically, August 30th, we put the lime and the fertilizer on for the following corn year, 2012 corn year, and then we immediately planted a cover crop of Austrian peas and groundhog radishes. The peas didn't do much, and we haven't figured out quite what the problem with them are, but the radishes did all right, but were hurt a little bit by the wet weather last fall. And then in the spring, before we planted, we killed whatever was growing there, which was a little bit of weeds and a lot of volunteer wheat, and that's something that's overlooked often, is volunteer wheat isn't really a bad cover crop as long as it's spread out across the whole field. If a combine has a chaff spreader on it, it does a pretty good job, really. Well, anyway, we had to spray it, and then on the 20th of April, we planted it, and I think they put the ammonia on about the middle of May, which is historically early for us. Usually it's more like the plant in May, ammonia in June, because of the dry weather. After the corn is harvested this fall, the way we used to do it, we'd put our P&K on for the next year and then not do anything else to the field. We found out that there's a lot better control of the runoff if the corn stalks are left standing. And a lot of people that have chopped or did something to them, if we do have a flood, they end up in a big pile at the lower parts of the field, and then they're where you don't want them, and they're harder to manage. So what we've been doing is then in the spring, apply a burn down to the field, which is doesn't include Roundup. It includes some residual herbicides to keep good weed control. And then right before planting, usually a few hours, we go over it with a vertical tillage tool to kind of spread the residue out, knock it down so the planter works better. So we haven't touched the ground at all yet since the wheat was planted no-till. We're trying to keep it. We found out that the no-till promotes biological activity, and the soil structure just gets amazingly better after a few years. And maybe that's part of what Mr. Scavia was talking about. We're getting water to move down through the soil profile that we didn't used to. It used to stay there on top. So we're going to have to figure that out, because the crop production from properly managed no-till field just seems to keep getting better. And then after the beans are harvested next fall, we will put some phosphorus, potassium for the wheat crop, and about 30 pounds of N to get the wheat going. That's usually put on right before planting, plant the wheat, and then the wheat's there the whole year. And we don't top dress the nitrogen on the wheat until the following spring, usually at the end of March through most of April, sometime in there. And sometimes we have included medium red clover and sweet clover as a cover crop, and that really works better than the Austrian peas and the radish if you can get it to grow. This spring, a couple fields we put it on, it was too dry. A lot of that clover died. Some years, if the wheat's really good, it crowds the clover out. But in an average year, under average conditions, you end up with a pretty good seeding. I think I got a picture of that. Yeah, up there on the top where it's between the straw windrows, that's clover and sweet clover. And it really makes a nice field to plant in. The other advantage of it is if you do put the fertilizer on in the fall, you got something growing there already to suck up anything that's available. So that's what we've been trying to do, at least on that one rotation. And there's some of the challenges to solving this problem is to possibly keep the dissolved phosphorus from moving through the ground. We might have to incorporate it, but we really would rather not do that if we didn't have to, because it could cause some compaction, could cause some soil structure loss, and it takes extra people, and if the weather's against you, you might have trouble getting it done. So we're trying to think of different ways to do this. I mentioned before, having our own fertilizer storage so we can still buy it at the right time of the year, but instead of storing it in the ground, storing it in a building. Having some application equipment of our own so we can put it on right after planting, so the likelihood of something being there to take it up right away is greater. and then drainage management. And I think this is where a lot of work needs to be done, because I think we could really help ourselves with either drainage control structures, which is basically blocking the end of the tile up when you don't need the water to run out of them, or building reservoirs and using that water then later in the summer when it gets dry to put water back on the field. And I think in the future that's something that you're going to start to see in the Great Lakes area, because we do have times of dry weather and we could use the water, and by holding the water back, it doesn't make it to the lake and carry all that bad stuff with it. It would put a lot less stress on all the harbor infrastructure and drainage ditches. You know, a lot of places the drainage ditches would be adequate if they weren't forced to take everything all at once. So I think that's an area that we could do a lot of good on. How's my time?
You get one and a half minutes.
Okay. All right. And I had this slide put in just in case, but I guess we're going to have that later. But anyway, here's a picture of our bean planter. And I think if we work at it, the technology is getting better all the time. We're planting after our rye that we pre-cut and harvested the straw off of. He's planting beans. This is probably about the middle of June. And the tractor has GPS on it and RTK, which is a way of steering the tractor. And it is accurate enough that he's able to plant the 10-inch bean rows between the 10-inch rows from the year before. He just moves it over 5 inches, and the planter works a lot better, and you got these nice little dam up and down between all the rows. So if we have a storm after that's planted, it'll stop the water a lot better. I think that's it. Thank you.
Thank you very much. It is my great pleasure to call up next Melissa Malott with Clean Wisconsin. Melissa is an advocate and lobbies for the protection of clean water regulations, for the enactment, and I'm very excited to hear her story of what's happening in Wisconsin with the phosphorus rule, non-point source, and point source pollution requirement reductions. So I have Melissa ready to go. She got her law degree from the University of Wisconsin, and we will have her PowerPoint up very shortly. Thank you very much.
Hi there. I want to thank you all for having me today. This is an exceptional honor, and I am really excited to be here. I'm going to err on the side of being concise, assuming that we'll ask questions later if I need to clarify anything. And I just want to note that nutrients are really complicated, as we're seeing from the scientists today. It's taken decades for states to address this, and I propose that Wisconsin's new phosphorus rule that we passed in 2010 and are implementing now can serve as a model. As we get into this, I want to propose that there's 4 reasons or 4 barriers that typically cause watershed plans or cleanup plans to fail. And those 4 reasons can be categorized, I believe, in terms of a lack of data, a lack of financial resources, a lack of relationships or political will to clean up water and do what needs to be done, and finally a lack of a proper legal framework or accountability. So thinking about that, as I go through my presentation, I'd like you to think about the dynamics that this is going to change and how this rule works, the dynamics that it will set between different players and how that might work in your state or area. Just so you know, this is an overview of what I'm going to go over. I'll go over Wisconsin's phosphorus rule, how we're implementing it, and what I think the takeaways are for other states. And just really quickly, numeric criteria set a limit for how much pollution can be in a waterway. And the way that permittees usually comply with that is that they use technology upgrades to limit their discharge of that pollutant so that they do not cause or contribute to an exceedance of that water quality, of that pollutant in water quality. Typically, they do this through technology or trading sometimes. And what Wisconsin's water quality standard does is it creates a new option for them. This is called the Watershed Adaptive Management option, and it's just another way for them to comply with permits. What they get essentially is a different way of looking at that equation of water quality plus their discharge needing to be less than the water quality limits. Usually where permittees look at their own discharge and limit their discharge through technology, under the Watershed Adaptive Management option, they're looking at existing water quality. So they get 10 years, essentially a 10-year pass to figure out non-point source controls to make it so that water quality plus their discharge can be below water quality limits. At the end of those 10 years, if the water quality standards if water quality is not meeting the standards, then they will have to focus back on their discharge and limit it through technology upgrades. Those technology upgrades are very expensive. And so what Watershed Adaptive Management does is essentially puts the responsibility for clean water on the permittees. And you might ask why they would want to do this, and they're driven by cost and risk. For technology upgrades for a plant in my area, which serves 250,000 people, meaning a wastewater treatment plant that serves 250,000 people, it would cost about $200 million over the course of 20 years for them to put in phosphorus control technology. That's a very expensive technology for one source of pollution and one type of pollution. So thinking about that cost, they are going to be driven to do watershed adaptive management and clean up our watershed because it will be much cheaper in the long run, we expect. So cost is a major driver for this. These are the elements of the plan, and essentially you can divide these into 3 phases. They need to look at what information they need to figure out what to do in the watershed to get phosphorus pollution from non-point sources cleaned up. They need to analyze that information, and then they have to figure out a plan. And this is the part that I think is pretty critical. These elements are pretty straightforward and basic, and we have a lot of certainty for our permittees that they have to meet water quality standards. So there's certainty for them about what the goal is. And there's also a lot of flexibility in how they get there. So I think that because they're driven by cost savings, and because there's clear accountability to water quality standards, that this can result in a situation where we can overcome those 4 barriers to watershed plans. The point sources will be driven by finances, so they will make sure that there's the money available to actually clean up the waters. They'll make sure that they are working with universities and other scientific resources to make sure their data is accurate and that the information they're basing their plans off of is accurate. They'll work with local governments and state governments to make sure that there's the political will to actually get this done, and they'll work to set up a regulatory framework or legal framework so that there's some accountability between them and non-point sources. That accountability can come in the form of existing agricultural standards. It can come in the form of passing new local standards that are appropriate. For example, in the watershed I live in, the biggest source of phosphorus is winter liquid manure spreading. And if we were going to, we've talked a little bit about trying to ban that or making a better ban than we currently have. To do that, though, we would have to figure out a way for farmers to store their manure. And so figuring that out is all part of what we're doing with the pilot project that we're working on. Very quickly, I just wanted to point out the difference between watershed adaptive management and trading, and I'm sorry about the font. Basically, watershed adaptive management is different because it's more about water quality and actually achieving water quality standards, whereas trading is about point sources being able to offset their discharge plus some environmental good. It's pretty vague. And I think the really important difference between watershed adaptive management and trading is that there's more certainty with watershed adaptive management about what the outcome is supposed to be and about the flexibility that they have to get there. So where are we at? This is a picture of me working with one of the agricultural leaders in our community. His name's Jeff Endress, and he has a 300-cow dairy that is part of a co-op that requires high environmental standards and ethical treatment of animals and fair labor practices by the farm to sell their milk for a premium. And then the person on the left is our local county conservationist. And for a lot of states, that's the equivalent of a soil district manager, I believe. Basically, we have a couple of watersheds in Wisconsin that are moving forward on this at this point. One is a very small watershed where it's a 16,000-acre watershed, and there's one medium-sized municipality, and the wastewater treatment plan of that municipality knows that they can take on the cost and the risk of cleaning up that watershed, and they're working with their local county conservationists to come up with a plan. I think that they'll be the first one to enter watershed adaptive management in Wisconsin. A medium-sized watershed is the one that I live in. We have one very large point source, that's our wastewater treatment plant, a couple of small point source dischargers, and then a lot of municipal stormwater utilities. And we have a TMDL that is driving the municipal stormwater utilities to want to be part of this plan so that it mitigates costs and has everyone in the same risk category and lets them come into compliance with their permits. And then there's a very large, complicated watershed, which is the Fox-Wolf Basin, looking at this and trying to move forward and figure out how it would work. And there's many, many point source dischargers. It has the biggest concentration, I believe, of paper mills in the world and the biggest concentration of CAFOs in the world. And figuring out how to get all of the municipalities and industrial dischargers to work together is going to be complicated. Where we are with a couple other points, the DNR is kind of confused about how to use this. They're under-resourced and they have a desire to move forward. They've done some internal guidance for permit writers to know how to implement this, and they're working on a technical guidance for permittees, but there's a lot of staff that don't fully understand it, and the burden of doing education and outreach both for internal DNR staff and for permittees is falling on the nonprofit community to figure out which watersheds we should focus on, how to do education and outreach to permittees on coming into compliance for this, advocating that they do look at this in the first place because many of them don't understand it. And we're doing that by figuring out which watersheds to target that we think would be feasible and working on a handbook to allow them to understand how it will work. Many municipalities and POTWs around the state are publicly owned treatment works, and some industrial leaders are moving forward and trying to figure out how to get this to work in their watershed. I'm optimistic about a couple points, and I think one of the most important is that when you think about the ways to reduce phosphorus runoff, like putting in vegetated buffers, those things have additional benefits. Vegetated buffers have habitat benefits. They'll make it so there's potentially more biofuels that we can use in the state. And with each of those co-benefits, you can incorporate more stakeholders and more potential funding sources. So when we think about watershed adaptive management being just a set of permittees worrying about their permits, in essence it is, but in the bigger scheme of things, it will be much more collaborative and bring many more people to the table to participate in what it looks like. And I have a vision of these plans incorporating stakeholders who have other goals, and they can figure out how to dovetail those goals with this. So if we have a Audubon Society locally that wants to work on more wetlands restoration and for bird habitat, they can potentially work with these watershed adaptive management plans and bring money and resources or just people to support the project and merge that with the phosphorus reduction plans. So I think that these plans can be very big, and I'm optimistic that they can accomplish a lot in our watersheds. Some of the issues that we're watching as we move forward are how TMDLs will play into this. If a TMDL is written and it puts all of the burden of the TMDL on non-point source polluters, point sources would potentially not have to limit their discharge and would potentially get out from under doing watershed adaptive management. So I'm hopeful that the EPA and DNR will make sure that the TMDL load allocations and waste load allocations are properly allocated to allow watershed adaptive management to move forward where it would be appropriate. Some of the weaknesses or things I'm worried about are if phosphorus control technology becomes very, very inexpensive, there won't be a driver to move this forward. If DNR is unable to keep up with permits and keep this moving forward, we're going to face problems. And finally, you might have heard about Scott Walker, our governor. He has tried to roll back this rule, and fortunately the EPA has been very supportive and stayed behind us, and we've been able to protect the rule in collaboration with some of our partners and permittees because they like this option. They want it to be there available for them, but we need to keep watching that. And just takeaways for everyone that I wanted to note. Getting this rule passed took a very large effort, and in it we worked with the environmental community was extremely coordinated about our strategy. We coordinated with the DNR in some ways about what we were going to do and what we wanted them to do. We were very clear about our communication with them. We also played our hand under the Clean Water Act. EPA has a responsibility to make sure that states move forward on setting standards for certain pollutants. And so when, as we were thinking about the strategy, some of the environmental community sent a letter of intent to sue the EPA to make sure that the DNR was moving forward on setting these pollutant standards for phosphorus. We also worked for 2 years on the side with some of our industrial groups and our wastewater treatment plant partners to talk about what this rule would look like. And we heard for 2 years what they were concerned about. They were worried about the expense of the phosphorus control technology, and they were worried that them putting in these technology upgrades wouldn't make a difference in water quality for communities because so much of the non-point source pollution, or so much of the pollution is from non-point sources. So they're worried about spending hundreds of millions of dollars across the state to make a tiny dent in phosphorus water quality. So those were valid concerns, and we thought about that, and we thought about how to shape this so that it would work for everyone. As we worked through that, we shaped the rule by looking at what works and what doesn't. So I've talked about those 4 points that typically trip up watershed plans, and we tried to think about how to set up a rule that would overcome those barriers, and I am optimistic that we've done that. We wanted to make sure that the rule would have accountability, and it does. We wanted to make sure that it has certainty. It does. We wanted to make sure that it had flexibility. And one of the other things that I think is noteworthy for other advocates is if you move forward with this rule, you have to work with the DNR about how it's going to get implemented. There's been a lot of confusion about who's playing what role and how certain processes will play out. So there's a lot of, this rule is very vague in some ways in that there's a lot of flexibility, but it also means there's a lot of different scenarios about how it can play out in different watersheds. We don't have yet a process on how to figure out that, and as we move forward on some pilot projects, there's been some miscommunications that have been kind of frustrating, but if you move forward, I think working with the state on it would be very helpful. And I'm sorry I went over my time, but I'm all wrapped up. Thank you.
Thank you, Melissa. I really think that her 4 points of the need for data, the need for funding, the need for strong relationships and accountability really tees up our final speaker very well. Chief White has been with the Soil and Water, has been with the Natural Resources Conservation Service for over 35 years. He is a dynamic leader and the right guy to be leading the service right now in this moment in history. And I look forward to all the exciting overview of what the NRCS is doing for the Great Lakes and touching on the critical issues of till or no till. And take it away, Chief White.
Well, how do I tell? Okay.
That's good.
Okay.
You put it straight with your
Thanks. Greetings, Earth creatures. It's grand to be here. Which is the clicker? Oh, I figured it out. I used to be the state conservationist for NRCS in Montana, and this is the view from not quite my house, but a few minutes drive. You're on the Highlight Mountains, and you're looking at the Spanish Peaks there outside of Bozeman. And I got the call from Secretary Vilsack asking me if I wanted to head up NRCS, and first I had to make sure that it wasn't one of my inebriated friends playing a joke. And I finally was convinced that it was him, and I said, all right, you want to put me in charge of 12,000 people and $4 billion, and the mission is to do good? He said, yes. Yes, I can do that. And then I said to him, thank you, Mr. Honored to accept that challenge. So anyway, I talked to my wife. She was cool with it all. Of course, we don't get out much. We didn't know what kind of provisions would be on the way east, so we loaded up the car and headed out this way. So remember, this is what I used to look at, and this is what I look at now, and I go, I've screwed up. But anyway, I was able to get a few licks in, and one of the key things we were able to do is start landscape-level initiatives. Instead of spreading this money out, doing random acts of conservation, actually start targeting so you like accomplish something. It did cause me some health problems. I had to go see a plastic surgeon and get a rear end enlargement to make room for all the boots that were being applied. Because there were some members of Congress who did not like this at all. But all the science is in, targeting works, systems works, conservation works, and now it's kind of a mood issue. And these are the ones that are just kind of the water quality stuff, and we'll get into your stuff a little bit later on. Any cropland field in the upper Midwest, what's attached to this water when it runs off? Everything we put on it. And in this particular area, it collects in this place called the Gulf of Mexico, the dead zone down there. We've heard a lot about that, but this is what it looks like under the water when you don't have oxygen and you're from the planet Earth. So we're targeting in the Mississippi, we've got like 640 12-digit watersheds. 12-digit watersheds, about 10 to 40,000 acres, 123 different projects. We've got an average of 9.5 partners per project, and this year we've already put in the last 3 years $222 million devoted to wildlife habitat and nutrient management in these areas. This is your alls area. The green area here is where we're really starting to focus on phosphorus, which a lot of people have mentioned. I got to give a little shout out to my friends here at EPA. Last 3 years, they have transferred $75 million to us. We put into this about 25 a year. This last year, we took 10 million of that and was all targeted towards the phosphorus. So I'm very grateful to EPA, and I'm simply saying that so you keep transferring money. All right, you saw this from the doctor's presentation, the algae blooms in Erie. That's what it looks like up close. This is good old Grand Lake St. Mary's. It's kind of on the periphery here. But let's talk about what we're doing about this stuff. And I'm going to show you a few before and after slides of the conservation work that's going around in our country. And you're just going to see a top few threads of a rich tapestry of conservation that's being woven in our country. But time says I'm going to be quick, so I'm going to be quick. Okay, classic gully erosion in cornfield today. Here's an abandoned poultry house. We're actually paying to dismantle these things, grind them up. We take them out, apply it in a cropland field to the soil according to soil test. Then we're taking putting soils back in where we're taking them off and reseeding them. No need to tell you what this substance is, this feedlot today. This is runoff direct from a dairy today. And we are also, please note, we're trying to get native species in here. We'd like to help our pollinators out so we have sequentially blooming plants so they have a longer food supply. Another area where cows right up there in the riparian area today. Can anyone tell me what those white tubes are? Tree protectors? No, no, no. We are so concerned those are actually nuclear-powered cow pie methane flares. Because we're trying to do our part for, you know, global warming, too. Actually, if there's anybody here from Missouri like me, those are tree protectors. The other thing sounds better, though. All right, this is an orchard guy. He wanted to take some ecosystem services and get them for free to help pollinate his orchard. Boom. I think I want to be buried here. This is gorgeous. This is Michigan. Really bad pasture. You see the cows down there. It's all messed up. Now they got a heavy use area plant. The pasture's reseeded. Better for wild quality, better for the producer. This is an interesting one. Superfund site in Michigan. EPA actually contracted with us. Chock full of cadmium, every other heavy metal you can think of. This is today. Farming right up against the edge of the creek. Boom, today. Get that buffer in there. All too typical scenario. We can fix these things. I'm going to show you some new technology. This little thing on the right, I'm not going to mention the name, but this is an actual infrared scanner. As you move across the field, it reads the chlorophyll level in the plant and will adjust the nitrogen and phosphorus to meet the plant's needs on the fly. It's going to have a huge impact and save us a lot of excess application. Dr. Josh McGrath, University of Maryland, is trying this. These cages hold steel slag. And this pond on the right is catching the runoff from 4 poultry houses. And we're finding out this slag stuff just absorbs phosphorus like crazy, something like 80–90%. So this may have some application in the future. Then we also got, they look like bowling alleys, but there's a solar pump and a drainage ditch. It's pumping the water down these raceways, and it's growing algae. Either take the nitrogen and phosphorus out. We're trying to figure out what to do with the algae. We think we may be able to burn it for fuel. I'm going to talk about soil health now. And our agronomists are going to have to get together with your agronomists, because I'm going to push back a little bit, because we're actually promoting never-till. And here's why. This is a farmer-led effort. You look at the guy in the lower left, Gabe Brown. He has not used any manufactured nutrients in 15 years. He's really cut down on it. Dave Brandt in Ohio has had a 75% reduction in the chemicals he's using. This is where we're messing up. This soil is naked, hungry, thirsty, and running fever. We're seeing huge temperature increases below the surface. We have completely converted the soil to an aerobic environment. We need to fix that. If you look at the natural soil organic matter, 4.3%, 17 years in a conventional soybean rotation, you're down to 1.6. If we can keep that soil covered, if we can keep a living cover on it year-round, and we keep roots, we get better water infiltration, the earthworms come back, the good bacteria comes back, we need less fertilizer, less inputs all the way around. Here's a cover crop. Our farmer here talked about some of this. Look at the piece on the left. You can see the weeds coming up. On the right, they're not coming up. Don't have to use fuel to go over it. Don't have to use chemicals to kill it. Let me just show you some drought pictures. The soil health is on the left. Same field. Same area, different field on the same day. 11 years continuous no-till and 2 years of cover crops versus the field across the fence. Here's 11 years no-till plus 5 years cover crops across the fence. And by the way, this dog is 8 foot tall at the shoulder. There's a rancher down in Missouri, my home area, and he's been doing this soil health. He does mob grazing. This is last year. Look at what his cows had and what his neighbor had. We can fix these things. We can fix them in harmony with agricultural production. And I think that's the key thing here. We've got 9 billion people coming to our planet. We're going to have a 60 to 70% increase in food production. And how are we going to do that and have clean air, clean water, abundant wildlife, and a healthy environment for all of us? That's going to be one of our key challenges. And I was on the 2002 and the 2008 Farm Bill. In 2008 was loaned to Senator Harkin, and in 2002 to Senator Lugar. And I want to tell you one story before I close about the 2002 Farm Bill. And this was in the summer of 2001. This was before 9/11. It was before anthrax was sent to Senator Daschle's office and shut down the Hart Building. And I was living in Fredericksburg at that time and commuting via the Amtrak. And at that time, the last Amtrak train that left Union Station left at 7 p.m. So if I didn't get on that, I was sleeping on the couch or imposing upon a friend. And one day I looked up, it was early summer, and it was like 10 minutes to 7. Oh my God, you know, so I throw all this stuff in, I go running down out of the Dirksen building, down the hill, across 18 lanes of traffic. Long story short, I just barely made that last Amtrak train. And I'm sitting there and I'm all hot and I'm sweaty, I'm huffing and puffing. And the beautiful thing about Amtrak is they have this thing called the cafe car. And I'm in agriculture, and I really want to support agriculture. And one of the ways I support agriculture is through the consumption of value-added barley products. And the cafe car has these. So I went back to the cafe car. And and there's this little girl in front of me. I don't know, it's 8, 9, 10. I can't, you know, it's a little girl. And she's ordering this thing and that thing, and the lady behind the counter is putting it all together. And then I looked at her closer, and I know she is she's a Down syndrome child. And I don't know if you have any experience, but these are really wonderful people, kind, trusting, generous, much better people than I will ever be. And she had finished her order, and the lady got it all together and tallied it up, and she said, well, that'll be $6.74. And I saw this little girl's hand go up, and in her hand, she had $2 and a little skiff of change. And as I looked at her, she looked up, and she said to that lady, she says, is this enough? And I'll never forget the response, because this unionized Amtrak employee took that money from that little girl, and she looked down at her and she said, yes, honey, this is exactly right. And what I submit to you is that what is happening to our environment is happening on our watch. There is no one else to call. If these problems are fixed, we will be the ones to fix them. And I submit to you that that lady did that which is right. And in our time and in our place, we must do that which is right. For the environment, for each other, and for those little ones who will surely come after us. Thank you, and God bless you.
Is that the encore?
I got it.
Oh, thank you very much, Chief White. Thank you for everybody. We have a couple of minutes for questions, and so I'm going to ask folks to go to our microphones, which are located here. If you're by a microphone, you can wave your hand and direct folks to come over by you. That would be helpful. And while you assemble yourself to ask our esteemed panel some great questions, we're going to get started with a question that was previously submitted by Lyman Welch from the Alliance of the Great Lakes. So panel, what programs or policies do you see being realizable in the near term to significantly reduce agricultural sources of nutrients? And so I'm going to ask you, because I'm sure there's lots of programs and policies, so you each get one. What's the best program? Chief, we'll start with you.
Well, y'all heard Tina May from Senate Ag Committee yesterday, and I think she's a rock star, and so is Senator Stabenow, you know, for the environment, and we've got a great committee. Senator Brown is on there as well. My weapon of choice here would be the Conservation Stewardship Program or the Environmental Quality Incentives Program. It's hard to really, pick one out because it depends on the producer, the landscape. Maybe the wetland reserve is that. Maybe we need to just keep this land in ag. So it's as varied as the number of producers. And thank God we've got a good diversity. We've got, thanks to Senator Stabenow and Senator Roberts and Representative Lucas, Representative Peterson, the respective committees, we've got there's very little disagreement in the Farm Bill on Title II. We're going to have a lot of tools and the ability to effectively address these issues.
Excellent. We have a number of folks that have lined up. Is there anybody else at the panel that wanted to speak to one program or policy?
I'd just like to make a comment that, and I appreciate what Mr. White just said, but we're still having a problem getting everybody in the door, and I don't know how we're going to resolve that. I don't want to be pessimistic, but we got to work on that somehow. Because there's some guys that just don't pay attention.
She's taking care of that.
And Melissa?
Yeah.
Our former Department of Ag secretary said that getting something done takes a three-legged stool: education, economic incentives, and enforcement. And making sure that we're taking an approach that is comprehensive and addresses all of those is important.
Excellent. We're going to start over there with you first.
Gito Torrey, Ducks Unlimited. Question for Don Scavia. Dr. Scavia, have you looked at analyzing any of the wetland loss impacts in the Western Lake Erie Basin, and what modeling what might be an advancement in terms of wetlands and their benefits of reducing phosphorus, nitrates, sedimentation, modeling the BMP advantages of wetlands, if you will?
So we haven't looked specifically at that particular point, but what we have done is we've used these SWOT models to indicate where best practices would make the most impact, depending on whether you're looking at particulate phosphorus or a soluble reactive phosphorus load. And as you can imagine, the wetlands near the mouths of the rivers near closest to the lake are the most important ones from that. Whereas upstream, there are other buffer strips and other things that would probably make more of an impact.
Thanks.
Excellent. Is that right?
Yeah, the last speaker alluded to this, and it's a question I've been wondering since last summer, and that is, in other parts of the country, people are looking at algae as a biofuel feed source, and I wonder if anyone's looking at harvesting the algae problem in the lakes as a biofuel.
As horrible as the algal bloom looks here, it's really not, my understanding is it's not really high enough abundance or extractable to be a sufficient biofuel. If they were doing things on the land, like you were talking about, with sort of capturing it before it gets into the lake and building really high concentrations in small pools, it may be more productive.
In the back?
Let me address that. I actually attended a whole conference in Worthington, Minnesota, where they talked about this, algae, and what we might do as a fuel, and we're a long way away from being able to commercialize that, make it profitable.
Thank you. This question is for Dr. Scavia. I'm Doug Inkley, National Wildlife Federation, and a Spartan.
That's okay.
You mentioned at the very end of your presentation the new challenges of climate change for the lake and how things are different. I assume that what that means is that the practices that are in place will need to be done more and better, but do you foresee any other practices, some changes in practices? What do you think is the most important thing to reduce that impact?
So I think the biggest challenge is actually dealing with this excess water that we're getting in these very large storms. The natural tendency and the logical tendency is actually to put in more drain tiles because you've got to get the water off the land in order to grow the crops. So I think the biggest challenge is going to be figuring out what to do with the water once it's coming off the land. Whether it's going to be channeled through wetlands or other holding back before it gets into the lake is going to be the most important. And I think the biggest issue is going to be dealing with this large amount of water that we're seeing now, and we're going to be seeing even more in the future.
Thank you.
So I got my 2-minute mark. So I have two speakers, two folks that look like they want to ask questions. We want to move very quickly. I think we'll go with Sandy first.
Thanks. This is for Dr. Scavia. Also, what about the internal loads and nitrogen as an impact? Are you looking at that at all?
So there's been interesting new work looking at nitrogen internal nitrogen as a potential source of of using up oxygen. I'm not sure that that's actually going to play out to be a very significant source. As far as nitrogen in driving algae, the algae that are the most problematic right now are in fact not nitrogen fixers, which is so the nitrogen fixers become really important when you get lots and lots of phosphorus. And so I think the primary driver is going to remain phosphorus, and the primary solution is going to be reducing phosphorus loads. Can I make one? I want to make one just quick thing about no-till. I was not promoting getting away from no-till. No-till is important. It's doing very important things. I think the key message in yours was that the farmers that are using no-till that are no longer applying phosphorus. I think if we look at ways to actually do no-till and keep the phosphorus concentrations at the right levels, I think we'd be better off.
And sir?
Yes. Question for Chief White, Steve Taylor. I'm with the affiliate with the Fertilizer Institute. As you know, we've been promoting the 4R program, and in Ohio, the governor of Ohio, along with the fertilizer industry, has supported the 4R program. At NRCS, we appreciate you've included that into your 590 standards. I wonder if you want to just give a shout out for the 4R program, sir.
Well, absolutely, and as part of the adaptive management, the 4 R's are right time, right place, right method, right amount. If you get all 4 of those things right, then you're not going to have a lot of the nutrient issues. And we have worked closely with the Fertilizer Institute. I think we've got like a $250,000 agreement on part of the education. A lot of the fertilizer dealers are getting on board with this. So I'm very encouraged when a lot of people, I think we can whip these problems, and we can use our nutrients right, we can use them appropriate, we can grow the food we need for the burgeoning world population, and we can do it in harmony with a quality environment.
I want to thank our panelists and everybody that asked questions. Thank you so much. There is so much left to be done on nutrients, but we know that effective collaborations, continued investment, and having real standards that we're going to meet is what's going to be best for our lake. So keep doing the great work that all of you are doing. Thank you very much.